Okay, this is exam 1 for Physics 101. The first question is an approximation question. A rambit is an imaginary unit of measurement of length shown here. Estimate the area of this shape in square rambits. Okay, well, you're going to have to make this into two pieces. One is this piece right here. And if this is a rambit, then this is going to be one rambit. That's about one rambit by about two rambits. So this rectangular shape is going to have an area of two rambits. So we can get rid of immediately D. And then this upper part right here, well, this is a little bit more than a rambit. It looks like maybe 1.5 or so. Um, so I would say that this is about a half of a rambit. So the area of a triangle is 1/2 base times height. And so if this is about one rambit or a little bit more, and this is about one rambit or a little bit more, actually I think it's a little bit more. So really I'm looking at a little bit more than a half to maybe one rambit. So really the only closest thing that I have there is going to be 3 rambits. What is the area of your typical spacebar on a computer keyboard? Well, if you look at your spacebar, you should have it in front of you. It's going to be about 1 centimeter in width and about 10 centimeters in length. It might be a little longer, a little shorter, but it's definitely not 100 centimeters in length, which would give you 100 centimeters square. So C is going to be the right answer for number 2. This equation is dimensionally correct. What are the units of R? Okay, we've done these before. I'm going to solve this equation for R. I'll just multiply both sides by V and divide both sides by X to get a value for R. And so that's going to be AV cubed over XT. A is meters per second squared. V is meters per second, but it's cubed. And then I have 1 over meters and 1 over t, or 1 over seconds. And so I get rid of one of these meters, and I'm left with meters cubed over seconds to the 6th. Where's that? A is number 3. Which of these equations is dimensionally correct? Okay, so let's do the units for this first one. I'm going to have meters squared per second. That's xt. Where the 3 doesn't matter there. I have meters per second squared, meters, and seconds. So here, one of these seconds cancels out with one of those seconds, and I'm left with meters squared per second and meters squared per second. So this one checks out. Number 2 I can look at and tell right away that it's not an equation because this looks like one of my kinematics equations, and I should have a t squared there. But let's just disregard that and work through it. I have x is meters, v is meters per second, times t, which is seconds. Those cancel out. So far I'm okay. Plus 1/2 doesn't have any units, meters per second squared, and seconds. And here this seconds cancels with one of those, and so I have meters, meters, and meters per second. So that's not dimensionally correct. Number 3 is actually, remember I told you that there are actually 2 other kinematics equations that, especially if you're preparing for the MCAT, that you might want to know those. And this is one of those equations. So I know right off that it is dimensionally correct because it is one of those unspoken kinematics equations. So I have meters squared per second squared equals meters squared per second squared. These are the same units, except here I have a V naught, but that doesn't affect the units. The 2 doesn't have units, meters per second squared, meters, so all of those have meters squared per second squared. All right, so the answer there is D. How many significant figures should this expression have? It might be better for you to just work this out. So 3.2 times 41.4. Oops, sorry. That's equal to 132.48, which is going to be 130, divided by 102.4 minus 3. What is that, 99.4, which would just be 99, because I keep the lowest number of decimal places, which would be 0 decimal places. And so that gives me 2 in the top, 2 in the bottom, so C is the right answer for number 5. How many significant figures are in these numbers? Oh, let's see. Looks like I had a problem here. Which one did I intend? I'll fix this on your exam. Hold on. Yeah, I didn't intend this. I'll fix that. So 0.0030, that has 2 sig figs. This has 2 sig figs, just the 3 and the 2. This has 1, 2, 3, 4, 5 sig figs. All of them are significant. This only has 1 sig fig, the 3, and then this has 6. All of them are significant. So 2, 2, 5, 1, and 6. So C is the right answer for number 6. Which of these is not a basis for some standard of measurement? Frequency of a cesium atom, that's for time. Speed of light, that's for distance. Planck's constant, that's for mass. And so particular metal bar in France used to be a standard for length, but it is no longer. It's not a basis for a standard of measurement. Which of these is a standard for the kilogram? Silicon sphere was going to be a standard, but it was not used. The mass of the cylinder used to be the standard. It's not the fraction of the mass of the Earth. It's not the billion cesium atom. It's Planck's constant as determined by a Watt balance. Got some trig questions here for number 9. Consider this right triangle. What is the length of the hypotenuse? That's this leg. So I say the square root of 3 squared plus 2 squared is the square root of 13. And the square root of 13 is going to be 3.6. And then I also want to know, what is that angle theta? Since I have the opposite and the adjacent sides, I would do the inverse tan of opposite over adjacent. That's the inverse tan of 3 divided by 2. And the inverse tan of 3 divided by 2 is going to be 56 degrees. A piece of paper is 8.5 by 11 inches. What is the area of the paper in square centimeters? So 2 approaches you could do here. You could go ahead and convert these 2 numbers to centimeters and then just calculate it in centimeters squared. I'm going to do it differently though. I'm going to say 8.5 times 11. And that gives me 93 square inches. So there are 93 square inches on a sheet of paper. And then I'm going to convert that into square centimeters. 93 inches squared. I'm sorry, it should be 93.5, which would be 94 inches squared. Let me fix that. 94 inches squared. And now I need to convert that into square centimeters. I know that in 1 foot there are 12 inches. I have to square that conversion factor because the inches are squared. And then in 1 meter, there are 3.28 feet. To square that as well, I have one more. I need to convert meters into centimeters. In 1 meter, there are 100 centimeters. And that's squared too. And if I do all of that, I get the answer is 604 centimeters squared. Actually, the correct way to do this would be 600 square centimeters. I'll try to fix that. Let me make a note. Okay, and number 12. The speed limit on some roads is roughly 120 kilometers per hour. What is this in miles per hour? You need to convert that into miles per hour. 120 kilometers per hour. In 1 kilometer, there are 1,000 meters, and in 1 mile, there are 1,609 meters. If I do that, I get 120 times 1,000 divided by 1,609 is 75 miles per hour. Car is initially at rest. It travels 40 meters at an acceleration of 20 meters per second squared. What is its speed after traveling this distance? So first, I know that x is equal to 40. I know that initial velocity is equal to 0, because it says that. And the acceleration is 20 meters per second squared. And I want to know, what is its speed? I don't know the time though. I know that to find that speed, I have to say v0 plus at, and I know the acceleration, but I don't know the time. So I need to figure out the time. But I know that x is equal to v0 t plus 1/2 at squared. v0 is 0, so this whole term just goes away, and I have 40 equals 1/2 of 20. That's my acceleration times t squared. So t is equal to the square root of 4, which is equal to 2 seconds. So I have a time of 2 seconds, so my v is going to be equal to 0 plus my acceleration, which is 20 times 2 seconds, or 40 meters per second. So B is the right answer for number 13. You throw a ball up with an initial speed of 40 meters per second. How long does it take for the ball to return to your hand? Well, if it has 40 meters per second, that means it takes 4 seconds to go up to reach 0 velocity and then 4 seconds to go back down. So you might be able to think about this and just say, hey, it's 8 seconds. But I can calculate it. V naught is equal to 40. A is equal to minus 10 meters per second squared. I have this ball, it's going up and then comes back down again. I know that at the top, V is equal to 0. So I say V is equal to V naught plus AT. That's 0 equals 40 minus 10t. So t is equal to 4 seconds. Well, you might say, why do you put 4 seconds? Well, that means that it takes 4 seconds to go up to that distance, and then another 4 seconds to come down. So 4 plus 4 is 8. You throw the ball up, same ball. What is the maximum height that it reaches? Well, look, I've already found this time. So if it takes 4 seconds to get up to the top, that means that the height that it reaches I can find just by putting in that time. So that's going to be equal to 40 times 4 minus 5. What I did there is I just said half of negative 10. I got negative 5 times 4 squared. So that's 160 minus 5 times 16 minus 80. That's equal to 80 meters. Look, if I put in a value time for this, then it will return the position at that particular time. So if I know the time right here, for example, then I can just put in that time and it'll tell me the y position. I know this time right here is 8 seconds. Let's just look and see what happens when I put in 8 seconds. Y is v naught t plus 1/2 at squared. Now this is not part of this problem. I just want to, what if I put in a different time? What do I get? I'm going to put in 8 seconds because I know 40 meters per second times 8 seconds minus 5 times 8 seconds squared. That's 320 minus 320. So that's equal to 0. When I put in 8 seconds, which is the time right here, I get a position of 0. So with these parametric equations, if you put in your time, then you get the position at that particular time. So the trick really is knowing the time. And we can find the time pretty easily right here because we know something about the motion of that object at the top of the trajectory. And that is that the velocity of that object has gone to 0. You throw a rock straight up in the air as in this figure. The dotted line is halfway to the maximum height. Which of these statements are true? The speed of the rock is the same at points B and D. True. We could also say that the speed is the same at A and E. Those are very similar statements, and both of them are true statements. The speed of the rock is the same at points A and E. Oh, so A and E. So that's also true. The time for the rock to travel from A to B is the same as the time to rock to travel from B to C. So is this time the same as this time? They're the same distance, but initially I'm traveling much faster. In fact, the rock is slowing down as it goes up and then speeding up as it goes down. So it's going to take it's going to be a lot quicker from going here to here and much slower going from here to here. So this is not a true statement. And the acceleration at the top of the trajectory is 0. Also not a true statement. That in fact at the top the acceleration is always equal to minus 10 meters per second squared. That the velocity in this case is constantly changing at this rate of minus 10 meters per second per second. Now, the velocity at the top, of course, is equal to 0, but not the acceleration. So just 1 and 2 are correct. Runners, I like to run, they measure their speed by pace, and a good runner might complete 1 mile in 5 minutes with a pace of 5 minutes per mile. You run 1 mile. You complete the first half at 5 minutes per mile, and the second half at a 7-minute per mile pace. So let's look at this. Say, this is my first half mile, And then this is my second half mile. And I run this in 5 minutes, and I run this section in 7 minutes. And I want to know what is my overall pace. Now, you might be inclined to say, well, 5 and 7, the average of those two is going to be 6. But I show you here that I'm actually spending a longer time at the slower speed. And so my slower speed is going to overwhelm my average velocity. It's going to impact my average velocity more than my faster speed. So the average of these two paces is going to be closer to the slower pace than the faster pace. So the answer is going to be greater than 6 minutes per mile. We had a very similar question to this in the concept test relating to average velocity. And so when you go slower, it impacts your average speed more than when you go faster because you're spending more time at that slower speed. A car is traveling with zero acceleration. Which of these statements is true? The car will be traveling faster after 5 seconds. It has zero acceleration, so it's not going to be traveling faster. It's going to be traveling the same speed. The car's velocity will continue to change. Also not true. The car's displacement will continue to change. Okay, yes. Because it's traveling, I'll actually come back and make this more clear that it has a non-zero velocity. But assuming that it's traveling, that means assuming that it has a non-zero velocity. So 3 is the only one, A. And again, I'll put non-zero velocity in the actual test when you take this. Consider this position versus time graph of an object's motion. Which of these statements is true? The object is increasing its speed between B and C. Well, here at B, it basically has zero velocity, and at C, it has a non-zero velocity. So sure, that's true. The object has a positive velocity at E. No, it has a negative slope, so that's not true. The object is at rest at C and D. You might be able to make the argument that it is at rest at D, but definitely not at C. And so this could be correct if I said the object is at rest at B and D, but that's not what it says. The object has a negative acceleration between points C and D. Oh, I like this question. So here it has a positive velocity, and here it has zero velocity. So it has a positive velocity and it's slowing between points C and D. If it has a positive velocity and slowing, that means that it has an acceleration that is opposite the velocity, or negative acceleration. So 1 and 4 are the right answers here. Consider this velocity versus time graph. Which of these best represent the position versus time graph for this situation? Here I have a big negative velocity, and here I have a small negative velocity. So first, I'm going to get rid of the ones that don't have negative velocity, and I'm looking now for a big negative velocity and then a small negative velocity. So here the slope is big and negative, and here it's small and negative. Over here it's small and negative, and then big and negative. So B is going to be my right answer for number 20. Consider the graph of the object's motion for the next two questions. What distance has the object traveled at t equal 3 seconds? So I'm looking at a velocity versus time graph, so I need to calculate the area underneath it. First, I'll do this section. This is 1 by 4. 1 by 4 is 4 meters. And then I have to do this triangle right here. So I have a base of 2 and a height of 4. 1/2 of the base, which is 2, times the height, which is 4. That is equal to 4. So 4 plus 4 is 8. So 21 is C. Consider the velocity versus time graph. What is the acceleration at t equal 4.5 seconds? Well, first of all, I know that it's negative, so let's get rid of that. And I can find my rise. My rise goes from 0 to 4, so it's actually negative 4. And then from 4 to 5, so 1. So my rise over run is negative 4 over 1, or negative 4 meters per second squared. So this velocity versus time graph, what is the average acceleration? Make sure you catch that word between t equal 1 and 4 meters per second. So that would be V final minus V initial, 4 minus 3, over my change in time, which is going to be between 1 and 4 seconds. So 4 minus 1, that's 1 over 3, or 0.33. So D is number 23. This plot shows the position versus time. During which time period does the object have the slowest speed? So I'm looking for the one with the shallowest slope. And so you might be able to look at this right away and say that it has to be B, but let's just find the slope here. This one has a slope of 4, right? Rise over run. This one has a rise of 1, or negative 1 actually, divided by 2. I'm going from 1 to 3. Here I have a rise of 1 over 1, and then here I have a rise of negative 4 divided by 1, or negative 4. So the one with the slowest speed is going to be this one. And notice it is speed, not velocity. If it was the smallest velocity, I wouldn't really ever ask that question in that particular way. But if I was looking at velocity, the one with the lowest value for the velocity is the negative 4. But again, when we talk about velocity, that negative doesn't mean that it's bigger or smaller. It means that it's going in the negative direction. It's going down, or it's going to the left. So we don't usually talk about velocity in big or small in the sense of is it negative or not. Vector A lies in the xy plane as a negative x component and a negative y component. That means it's going to be in quadrant 3, right? And the x component is bigger than the y component. So this, for example, would be ax, and this would be ay. So the resultant vector is going to be somewhere over here. That means that it's above this bisector line. So if this is 180 degrees and this is 270 degrees, this is 180 plus 45, or 225. So the answer has to be between 180 and 225, which is D for 25. All right, number 26. Calculate the sum of these two vectors. I always love to draw a picture for these. It just helps me to think about it. 5 units at 30 degrees below the x-axis. And then 8 units along the positive y-axis. And then I'm going to draw it again, but I'm going to break that first vector into its x and y components. So the x component is going to be 5 cosine of 30. Which is 4.3. And here it's going to be 5 sine of 30. Sine of 30 is a half, so that's 2.5. And now I'm going to combine alike vectors. So all the y component vectors I'll combine, and it's going to be 8 minus 2.5, which is, what is that, 5.5, and then 4.3. And now I know that my resultant vector has to be somewhere in this first quadrant, although I'm not asking for an angle, but if I were, I could know that that angle is between 0 and 90 degrees. I'm asking for the magnitude of it, or the 5.5 squared plus 4.3 squared. And that's going to be you get 6.98, or 7 units. So number 26 is B. And now 27, almost there. Ooh, I like this one. Vector A is 110 degrees from the positive x, and vector B is 260 degrees from the positive x. Which of these vectors is a possible solution for the vector sum? And it can be, it is going to be more than one answer, because I don't give you a single answer. Let's draw it, okay? If ever in doubt, just start drawing a picture. Vector A is 110 degrees from the plus x-axis. So that's right about here. Right, this is 90, it's just a little bit beyond that. And then vector B is 260 degrees, so it's right about here. Right, this is 270, so 200, this is 110, this is 260. So my remaining vector is going to be somewhere in between. And so vector A is somewhere in between. Vector B is in the wrong direction completely, so is vector C, and so is vector D. But vector E is also a potential. So A and E. B, C, and D are completely wrong, but there's no possible way that those two vectors could add up to give either B, C, or D. But E is a possibility, and so is A. All right, one more. Consider these vectors. What is A minus B? All right, we've done this before, so I'm going to draw A, and I'm going to draw negative of B, and so the resultant is going to look like this. And so which one is that? That's D, right? So D is 28.